Matter is of course made up of atoms. From a microscopic subnanometric point of view, a crystal is necessarily inhomogeneous. However, from a macroscopic point of view, a crystal is homogeneous. The electromagnetic properties of a material are usually characterized by their macroscopic permittivity and permeability defined through the material equations. The use of a macroscopic theory is usually justified, stating that the wavelength of light is much larger than the interatomic spacing. The field is almost constant in an atomic length scale. In this paper, we address the question of the electromagnetic properties of artificial crystals made of particles of one material within a host made of another material. Can they also be described through a macroscopic response? If so, how can we calculate it efficiently? How can we account for the geometry of the artificial crystal and for the materials it contains? What is the nature of the resulting response functions and how can they be employed? To calculate the macroscopic response, we introduce an external current. We choose its direction, its wave vector, and its frequency. Consider the electric field and apply to it the wave operator, which incorporates the microscopic dielectric response. The result is proportional to the external current. We solve the equation formally and average it using averaging projectors. As the source in this equation is external, it doesn't have fluctuations due to the texture of the material, allowing the average to be simplified. The average inverse wave operator relates to macroscopic quantities, so it may be identified with a macroscopic operator. Thus, we start from the response of each component. We build the wave operator, we invert it, we average it, we interpret it as a macroscopic operator, we invert it again, and we extract the macroscopic dielectric function. We found an analogy between the average of the inverse wave operator with the Green's function of a Hermitian operator, even for dissipative systems. This allowed us to adapt a recursive, very fast procedure. The resulting response is not only a function of the frequency, but also of the wave vector, that is, it's a non-local response. Here we show a typical response. Although calculated for two dispersionless materials, it depends on frequency and has structure due to resonant multiple reflections at their boundaries. Intersecting the scaled inverse of the squared frequency, we can calculate the transverse photonic bands of the system. Similarly, we may proceed to calculate the longitudinal modes and other modes that may not be classified due to lack of symmetry. Our results agree with previous band calculations, but they yield more information and may also be applied to metallic and dissipative systems.